Okay, so thanks for letting me this lecture in PARI GP. So it's nice to be in Amphi Chaboty because Claude Chaboty was the thesis advisor of the thesis advisor of my thesis advisor. And so PARI GP is a computer algebra system. So it's different from GAP because it's more targeted toward number theory rather than group theory. So I will do a survey. So, okay, so maybe the most important is the PARI GP website. So it's pari.mat.ubordeaux.fr. So it's there. Okay. And so I expect you managed to install PARI GP, and so you can work on the example. If really nothing works, you can try the GP in your browser, which is here, which run in your browser. Okay. And otherwise, there is I put the link to the conference here, to the slide here. Okay. So this is the slide, and this is the GP code used in the slide. So if you need, you can copy paste. Because sometimes if you copy paste from the slide, there is some characters that are not correct and it doesn't work. So from the text file, you're sure that it's okay. Okay. So there are three parts. I will first explain what PARI GP is. Then I will show how to use it for lattices, and also for algebraic number theory if I have time. Okay, so okay. Good. Okay, so what is a PARI GP? So it's three components. So it's the C library that you can use to write a C program and for fast computation. And GP, it's easy to use shell that gives you access to the PARI GP function. Okay, so GP, it's also the name of the scripting language. And we have a tool which is GP2C that allow to convert a GP program to a C program that use libpari. Okay. So for this talk, we will only use a GP. It's important to know that the remain exist. Okay. So basic object. So you can try in your own GP interpreter. So it give you a flavor of what it does. So it's for number theory. So first thing we need big number. So factorial of 57, so this gives you this. When you do division, it gives you a rational number and not a floating point. So you see 2/6, it's a 1/3. Oh, okay, that means this is the historic of the result. That means when you do a computation, you store it in the variable percent some number. So then you can recall it. So for example, when you set person 1 to this, and when if you enter person 1, you will get back the result. Okay. So the complex number square root of 1 is written capital I. Okay. So we get 1 plus y square equal to I. You can have polynomial and rational function. And when you introduce a new variable, by default, it is set to the monic polynomial in this variable. So since we didn't x, then we get the x is polynomial in x. Okay.
Does it mean that PARI stores every object that you have computed in one session? If you have it
in interactive mode, yes.
Really?
Yeah. Well, you could disable that if you want, but in practice, nobody.
If you have a lot of huge computations, then you just run out of space. You can't throw anything away.
Okay, but only in interactive mode.
Sorry?
This is only in interactive mode.
Okay.
I mean, if you do a loop on one line, it still counts as one line.
Okay.
Okay. So usually a user will enter 300 lines and then they will go to sleep or something. You see, it's.
You couldn't do that. You just immediately run out of space.
not sure about that, really. So the third one is more complex. Mod 2.5, say it's a class of 2 modulo 5. And so it's element of the field with 5 elements. And so you cube it and you get 3 mod 5, okay? The next example, it's the same idea, but instead of integer, you have polynomial. So now you work in the field q of x over x squared plus x plus 1. And so you have mod x and x squared plus x plus 1 as cube, and you get 1. So the 1 mod this, okay? So this is a way to define algebraic element. And if you want a finite field, so you could combine the two techniques above, but it would be very unwieldy. So there is a constructor, ffgen, that builds a generator for here is for the field with 3 power 5 elements. Okay. And so you can compute this 12 power in the field of 3 power 5, and you get this in terms of the generator. Okay. So this is for exact element.
What is the finite field generated 3, 5, and then what does the apostrophe W mean?
Oh, this is okay. Okay. The code W say you want it to be printed W. Okay. So since you name it W, prefer it to be printed W. So instead of giving just 3, 5, you can give an explicit irreducible polynomial of degree 5 over F3 if you want. Okay? So no, this was for exact objects. So we also have an inexact object. So floating point. So if you ask pi, you get this. Log of 2. If you are not satisfied because there are not enough digits, you can increase the accuracy. For example, P100 increase to 100 digits, so you get this. So if you take the exponential, then you will get 2, 0, 0, 0, 0. And we have also another kind of approximate object, which is power series. So when you do a log of 1 plus x, since it's not a polynomial, you will consider it as a power series. And the default precision is 16 terms. So you get 16 terms. Okay, and when you take the exponential, you see that you get 1 plus x plus big O of x power 16. So that tells you what the accuracy is. And if you are not satisfied with 16 terms, you can instead of putting 1 plus x plus big O of x power 100, and you will get 100 terms. Okay? So this is the basic PARI object. So to give you a flavor of what it is. So now the documentation. Okay? So if you do a single question mark, you get the menu. So this gives you about what you can do with PARI-GP. So we have few combinatoric functions, not the main point. We have numerical function, polynomial, power series, linear algebra, transcendental function. We have sum, product, infinite integrals, this kind of thing. We have a function for general number field, we will see at the end of the talk. We have function of central algebra, for simple algebra. For elliptic curve, L function, modular form. You will see the other topic that is not listed here, but it's the most important one. Okay. Okay, for help, if you have, you can ask for the list of functions in some category just by enter a question mark and the number. And so, for example, if you you should list the final function when there is one of the first ones should be atan. And so you can ask what it is. So question mark atan, you get the Arctons effect. And we also have an extended help. You can call using double question mark. And then you get more information. Unless the extended help doesn't work for some reason, you should always use it. Okay? Okay, so okay. Okay, so if there is double question mark with some name of some of the documentation file. So for example, you have double question mark tutorials that you can read. We have reference card. And if you put triple question marks, that will search in the documentation to find a function related to the topic. Okay. Okay, so a point. So okay, polymorphism. For a lot of functions in PARI GP are polymorphic in the sense that they will try to do something, to do what you want on the data depending on their type. It's not a very good idea, but sometimes it saves a lot of time. So, for example, factor of 91, okay, it's an integer, so you factor over z, and so it tells you that it's 7, 1, 13, 1. So that should be read as 7 power 1 times 13 power 1, okay? So now if you ask for a factor x power 4 plus 4, since x is not defined, it's a polynomial, so you factor the polynomial over z because polynomial is in z. So you get this. Okay. Now, if you want to factor over square root of 2, then what you do is that you change the coefficient to being a square root of 2. So you multiply by this. So you say, so this is the minimal polynomial of square root of 2. And so this map it in the field with q of square root of 2. And so you factor, and then you see to get the factorization of q of square root of 2. And a, it's implicitly square root of 2. Okay? If you want to factor over the field with 3 elements, one way is to map it to 13 to the field by multiply by mod 1 13. And so there if I factor over the field with 13 elements. So okay. So for this function, we added a feature to avoid this, which is you can specify the domain as a second parameter. So you don't need to change your polynomial. You just say, okay, I want to factor this one on the field generated by this one. And you get the same thing. And the same here. This avoids some bug when the input are simpler coefficients than what you expect. Okay. So okay, quickly numerical summation, because there are a lot of functions for numerical summation. For example, this is to compute integral. You can have infinite sum. You can have alternate sum. Okay. And okay, the third example. So you have to be careful because this function can sometimes you can manage to solve a divergent, to sum divergent theories. So you get something, but it's up to you to know if it makes sense. So in that case, it makes sense because you see, you get actually the derivative of zeta at 0. Okay. So okay, so a bit in syntax we will use in this talk. So we have a comprehension. So if this is notation, you see with the bar, you say you want the n square for n in 1 to 10. So this is this. Or you can add a predicate. I only want for n prime, so you can write this. Okay. And also we have multi-affectation. If you write bracket AB equal to bracket 1, 2, that will affect 1 to A and 2 to B. Save a lot of time. So this is the control structure. There are a lot of them, but this is the basic. So you have the if, while, for. And you see in the GP syntax, everything looks like function call. There is no, you see, so you just write if of expression, one thing, comma, one thing, and while, for, okay? Okay, and the last point of this slide is that there is a configuration file, .gprc and Windows gprc.txt, and so you can add configuration things. And what is important is PARI size max. So PARI size max is a way to say how much memory you want to use. So usually you should put half the total memory of your computer, for example. So this way, this PARI will increase the amount of memory until you reach this level and not cross it. Okay? Hmm? No. You write. That's why it is written in the file gprc. So once it's written, you don't have to do it anymore. Okay? The reason it's not the default, that it's very hard to know how much memory has a computer. Okay? So if you don't do that, for some computation, it will say PARI stack overflow because it won't have enough memory. Okay? Question of this part of the talk? Okay.
It isn't available as a Debian package.
Yes, it is.
Okay. No, I'm doing it from your page anyway. It's okay.
Yeah, you can. It's PARI-GP. The Debian package is PARI-GP. Okay. So do you manage to do some of those examples? Okay, now I will speak of lattice. Sorry for me being fast. Nice time. Okay. So first, to deal with lattice, we need to have a bit of linear algebra. So we start by linear algebra. So something I did not speak about yet is vector and matrices. So okay, I do it now. So to define a vector, you do a V equal bracket the component. So there will be a line vector. And to define a column vector, you have to use this symbol to transpose. This is the tilde is the transposition. Okay, and contrary to gap, PARI-GP use the French convention. So everything acts on the left and not on the right. So and so the more natural vectors are actually the column vectors, so the one with the tilde. So for a matrix, you have the coefficient and you have the semi-comma to separate the line. You see, you get this. So you can multiply V by W, and then you get the scalar product. Since you multiply the line by the column vector, or you can multiply the matrix by the vector W. So you multiply the matrix by the column vector, you get this. And also, a shortcut that's useful, sometimes you need to have a vector with a component to be 1 to 10, and then you have to write 1.10 to get the list. Okay? So, component. Okay, so now to get component of the vector. So you do V bracket 2 to have the second component, for example. If you need several components at once, you can extract it using 1.2, meaning I want a component from 1 to 2. So we get a subvector of the vector. For matrix, you have to put bracket 2, comma 2 to get the element. But you can also ask for a line or for a column or for a submatrix by specify range. Okay. And so we also have constructor. So we can use vector to do the vector of the component 1 over I for all I, but you can also do it using comprehension. And the same for matrix. Can matrix, you give a formula for the coefficient n j, and it will give you the matrix. And you can also create a matrix with specific diagonal on twins, diagonal matrix. Okay, so matrix internally are stored as line of column. So you can concat, if you concat vector, you get a longer vector, and you can also concat matrix. And in 2 dimension, you see. So here, since this is a column, and this is a vector, so you see you get a matrix with two columns. So mat identity gives you the identity matrix, and mat concat, well, it's the same as above, so it's okay. Okay, so linear algebra. As I said, we follow French convention, we went on the left. So first, mat det is for the determinant. So M tilde is transposition, as I said. You have mat size to have the dimension. You have mat rank to have the rank. So as always, the computation is done on the, over the field of the coefficient. So here you get 2. Mat ker gives you the kernel. And so if you multiply the matrix by the kernel, you should get 0. And here we see the only one kernel vector, but it's returned as a matrix with one line. So far, so good. Okay, so now maybe we can start. So the first thing, when you have lattice, you can want to do LLL reduction. Okay, so I can give an example. First, I build lattice. So this is a kind of knapsack, kind of knapsack, this kind of lattice. That is, it's mostly the identity, except that on some column, it's a very large coefficient. Okay, so you want to reduce it. So this is a lattice given by this basis. So you use QF LLL. So this gives you the transformation matrix to get the reduced matrix. Or if you want, you can use the comma 3 to get directly the reduced matrix and don't compute the transformation. Okay? So you check that m times t equal to b. That is, you multiply the matrix by the transformation matrix, you get the reduced matrix. Okay, and it's say 1 because there's convention that when 1 is true, mean 2 in PARI GP. 0 is false and 1 is true. So when you do equal and get 1, that is means it's 2. Okay. So now you have the basis. So you want to compute the Graham matrix Q. So it's just m tilde time m, suppose of m time m. And note the Gram matrix. If you want to do the reduction, you have to use the QFLL gram. So it's the same as above, except that you take a Gram matrix. It's useful because there are a lot of lattices where you don't know the basis because it's not integral or something. And you can check that you get the same transformation matrix as before. Okay. Okay, now we will. Okay, so now we'll start with to do an example more interesting and more related to the talk. Now we have some basis. Okay, so first we want to experiment with the lattice E8 from Renault talk. So you have to define E8. So I could have given you the explicit matrix, but I would have taken all the slides because it's an 8 by 8 matrix. So I use this formula. Okay. So you use the function matrix. So you want 8 matrix with component I and j, and you say, okay, if it's coefficient 1, 1, it's 4. If it's a diagonal, but not, or it's a border, but not the end of the border, it's 2. And otherwise is 1. Okay? So this is a if statement, you see? And so, okay, this gives you the one definition of the A8, of the Gram matrix for A8. So first, you want to check that it's symmetric, there's no mistake. So you just check it's equal to its transpose, you get 1, it's okay. So you check the determinant is 1, so it's quite, it's radially modular. You can check the signature. So 8, 0 means it's totally positive. Good. So now you can ask for the minimal vector with QF minim. So the first two components, so there are 3 components. So the first one, 240 is the number of minimal vectors with A8, as we see yesterday. 2 is the norm, so they all have norm 2. And the third component is the vector of the 240 minimal vector. Actually, we only give half of them because there is the action of V on minus V. We identify them, so we give only half of them. So if we take the first minimal vector, you should get this, for example. And you can evaluate E8 on V, and you get that the norm is 2. Which is exactly what we want. We want the vector to be a norm 2, okay? Okay, so more thing we can do is we want to, is it a perfect lattices? So there is a function PARI GP with QF perfection that returns the perfection rank, which is the dimensions of the space generated by the X transpose X vector for all the minimal vector, as you see yesterday. And this gives you 36. Okay, so you could write the function manually, but it's a bit tedious because you have vector space where vector are matrices, so you have to do some. And 36 is equal to 8 times 9 over 2. So it means it's actually a perfect lattice. Okay? So now you might be interested in the number of isometry. So there is function QFauto that computes the automorphism group. And so the first component is the number of isometry, and we get this number, which is the same as in the Renault slide. Okay? So this still is a group with a lot of automorphism. And
G is a group. G1 is what?
It's a structure that defines the automorphism group.
What's the number? 6967.
Oh, this is the first component. Okay, because the convention is we put the first component to be the order of the group, and the last one to be the generators. Okay. And this is not a commutative group. There is no middle component. So so G bracket 2 is the list of generators. So we take the first one. This is this. And okay. So we check it's actually an isomorphism. So we have to compute A tilde time A8 time A, and it's equal to A8. It's 1, so it's true. So it's actually an automorphism. Okay? So maybe I should, there is a function QF auto export that exports the group to gap. So you get a matrix group in gap, and then you can maybe do something more clever than what you can do in PARI-GP.
And that's a function in PARI-GP or in gap?
In PARI-GP.
To a file or something?
Or? No, to a string.
Well,
And then the string you can write it.
right.
Yeah. To me, as a rule, I think it's better to that software provide export function rather than import function, because it's much easier to write export function. Okay? I mean, it's much easier for PARI-GP to write the result of its own data structure in a gap format or magma format, whatever, than for gap to try to parse PARI-GP, because it doesn't have the PARI-GP parser. So you see, it's much less trouble. So, okay. Okay. So yeah, it exports the file as a matrix group. I could export it as a permutation of the minimal vectors. I don't know. Okay. So no, we try to do something a bit more like more number theory. So modular. So when you have a lattice, sometimes you can build the corresponding modular form. So the function in PARI-GP MF from QF. So MF means a modular form. So that means you transform a quadratic form in modular form. So A8. So okay. So it's a bit complex function. It returns 3 things. So you put bracket. But we only need the middle one, which is actual modular form. So MF params give you what kind of modulator is it. And so 1 means it's level 1. 4 is the weight. And that this means a trivial character with integral coefficient. Okay? So since the determinant of A8 is 1, you get level 1, and the weight is half the dimension, so it's 4, so it's okay. So now if you have the coefficient, you get this. And you see that this coefficient is 240. This is because the coefficient of the modular form are the number of vectors of norm. So norm 0, of course, there is only 1. Norm 1 is this, norm 2, norm 3, norm 4, exactly. And so where it gets more interesting is that you can ask for coefficient for very large number. For example, for this, 100,003, and you get this result. And you realize that if you wanted to do it just by counting all the vectors of norm this, there are so many that we never finished. You see? But using modular form theory, you can do it because it's rewrite the modular form as linear combination of modular form with simple formulas. And so then you get okay. You get this. Okay? You can also have the L function of the quadratic form if you want, which is about the same, except the L function is the modular form. So it has the same parameter. So the O1 mean actually it means gamma c. That is the functional equation is between the function times gamma c. And you can ask for value, for example, at 0. You get -1. And it's a general fact that you get minus the value of coefficient 0 of the modular form. Okay.
And in 64, is it actually doing a computation to work out all the vector, or is the form? It's a. What does PARI-GP do to get 64?
Oh, okay, if I remember correctly what I think, he has to compute some values, and then there is something which is called the Sturm bound on modular form, which is two modular form have the same coefficient to some rank, and so then you do some linear algebra to, so okay, this is very easy example because the formula for the coefficient I think is very simple. I think the cube of the sum of the divisor, the sum of the cube of the divisor or something. So, but that's the idea that, okay, so question, so okay, so an exercise that maybe doesn't work because I don't know. Okay, you can try to do the same for this quadratic form. So this is almost the least lattices actually. This is a W23 lattice which is just inside the least lattices. I pick it because you can write it very compact way. Instead of writing on my slide a 23 by 23 matrix. Okay. So, yeah. Okay.
What do we? You want us to do the same? What does the same mean?
As the previous slide.
Okay.
Mais I should have. Okay. I hope it works. And so it's a very nice construction of a lattice because actually you start from the equation. Some of the you want the 1 square plus 2 square up to 24 square is equal to a square. And so this is the differential equation, and there is very few solutions. And from this solution, which is totally accidental, why the sum of the 24 first square is a square, you don't know. But it gives rise to a lattice that allow you to construct a lattice with very interesting properties. So there is some kind of the miraculous identity give rise to very interesting mathematical object.
What does in the second line, the second command do?
Okay. So this computes the Gram matrix.
Yeah, but the next bit.
This remove 2 to the last coefficient below.
It removes the last.
It removes the last. It removes 2 to the last coefficient. Do you see? So if you don't want to type, you can use you can download this GP code here, and at the end you have this. Okay, so you can just copy paste it, and okay, so I copy paste it here. Okay, so I get this matrix. And then, okay, so Q of sine Q. Okay, so far so good. Well, I skipped the minimal vectors because of QF perfection of Q. Oh no, this one wasn't work. This one worked, but we will need a lot of memory. Okay. Yeah, the second slide doesn't work because I should have put the least lattice. Unless I made a mistake somewhere.
Doesn't the least lattice, do you need the 1 as well? 1, 2, 3, up to 24? No, 2 to 24.
I don't know.
I thought this is the instruction.
We could work, maybe, I don't know. So if you have enough memory, you should, this one should finish. And you get it's actually perfect also. Okay. Oh, you mean I should put the 1 in the least lattice? I don't know. Is it interesting?
You're trying to get the least lattice, is that right?
Hmm?
You want the least lattice?
Yeah.
Yeah. I think that's the least lattice either, actually.
It is in the documentation, just really cumbersome. If you do this, then you should get the least lattice somewhere. Okay, so yeah, get the least lattice there. That's why I wanted the shortest formula. It was more fun. Okay. Okay, so we have the least lattice, and then you can try. ça va marcher. Ok, ça va marcher, et cette fois ça va marcher aussi. Ok. No. Okay, so for the Lich lattice, we get 1 and 12, of course, since the dimension is 24 and this is still unimodular. And if you do MF cof of f virgule 10, okay, so we get the coefficient of the lattice. It gets very large quite quickly. So, and okay, and so we can get the coefficient 100,003, which is this number. So of course you could not count the minimal vector up to that point. Okay, so okay, so maybe I will we'll move to the second part of the talk.
Is that a public access online PARI calculator?
And this is the GP. So it's the GP in your browser because actually GP run inside your browser. I mean, we compile GP from C to JavaScript, and so then your browser runs the JavaScript code inside. So, in particular, even if 1 million people decide to run this software at the same time, it's not a problem for me since I don't. It doesn't run on my computer. So, okay. Yeah. So, where is this nice? When you want to do plot, because the web browser handle plotting much better than GP, normal GP. You get nice SVG plots, and you can, you see. Yeah. So, for example, I give example below. There is a list of examples. You see, you can run. So the plot, for example, this one. Oh yeah. Does it work? Je sais pourquoi ça marche pas. Bon, écoute, okay, so I will to the next talk. So where were we? Non, c'est pas là. Ah, c'est là. Voilà. So algebraic number theory. So this is a tutorial for algebraic number theory of PARI GP. It's a bit the basic, the main reason for PARI GP existence. So the slide where co-written page will be here next week. Ah. Oui, oui, oui. So, okay, so we'll call for the documentation. So something we can do is to use the automatic logging function. So it's \l and the name of a file, and it will enter everything that that it print to this file. So at the end of the session, you can read the file. Okay. So if you are on the Windows, first you are better to call it temps.txt or something because it doesn't. And also, what you should do is you create an empty file temps.txt somewhere in your my document things, and you type \l, and then you drag the icon of your file to the GP Windows, and you drop it, and then the full path of the file will appear on the window. You can enter. And you don't have to find what the exact syntax for where your file is.
L is last command, is it?
Hmm?
L is for last command?
No, L is for log.
Oh, logging, okay.
L backslash L is for log. Okay. Okay, so there's two topics. I'm not sure we can do all of them, but first, how to define number field. So how to work with element of ideal, and then how to work with class group on units. And the other topic can do PARI GP, which is the class field theory. Okay. So number field, blah blah blah. So as I said before, you define number field as a quotient of Q bracket X by some polynomial. So we will restrict ourselves to a monic irreducible polynomial. So for example, this one. And first we have a function policy to check that it's actually reducible. Okay, we get 1, so it's true. As example of polynomial, you can generate cyclotomic polynomial. So it's allowed to build cyclotomic field. Okay. J'ai l'impression que ton micro est allumé. Non. Parce que il y a ta tête sur la vidéo, c'est pour ça. Alors, so Paul mode. So as we say, you can use mod to define element of Q of X or Q bracket X of f of X. So, for example, mod xf power 5 with this polynomial modulo this one. So that means that if you define alpha to be a root of this, that means then you have alpha power 5 equal to this. Okay, and you can use leaf to remove the mod because it's more readable. For example, if you take x power 15, you get minus 1. This is because the J was a 30 cyclotomic polynomial. So by definition, x power 30 is 1. So 15 should be minus 1. Okay. So now we might want to do the compositum of two fields. For example, the square root of 2 and square root of 3. So we use Paul compositum. And you get, actually what you get is the decomposition of the tensor product of the field. So here's only one polynomial, but in some cases there will be several. Here you see the tensor product separate in the product of two fields of degree 8. That means that there are two possible compositum depending on the embedding you choose. Okay. Oh yeah, you can also want to compositum of a field with itself, because of course one of the compositum will be the field itself, but if you have several embeddings, you can get other things. For example, if you do this, you get the field itself, and then you do the one when you the three roots actually, the Galois closure. Okay, you can ask for the roots of unity in your field. So in this case, so the format is always the cardinal of the group and the generator. Okay, so since we take this one, we see that there is 6 roots of unity, and the generator is the second one. So isomorphism, so you can check isomorphism of field using an NF-ism. So here we get 0, which is false. They are not isomorphic. Okay? And the second case, we get a vector, which is a vector of isomorphism. So the actually is isomorphic. Okay? There's also an NF-isync. We check whether a field can be included in another. So, for example, square root of 5 is included in the 5 cyclotomic field. So that say yes, there is a solution, there is 2 solutions. But if you have a square root of -5, they say no, there's no solution. Okay. So what you could do is to check that actually this entity modulo Paul cycle of 5 square is equal to 5. So subfield. So you can compute subfield. Okay, so that gives you the subfield by the minimal polynomial there. Okay. Okay, so we use the flag comma comma 1 because we don't want to print the inclusion because otherwise it would take all the slides. But if you want, you can have the inclusion. So in the second example, we have the inclusion. So this is the field, and this is an element of the big field that generates the small field. You see? So this is the inclusion of the small field in the big field. Okay? So we put a comma 2 because to say we only want the field of degree 2. Okay? Well, there is a variant for a maximal subfield, which is an F subfield max. We give only the maximal subfield. And they don't necessarily have all the same degree. So, okay. So the problem with all those Paul compositum, for example, you can't, sometimes you can get polynomials with rather large coefficient, which will slow the computation. So there is a function Paul red best that tries to find another polynomial which defines the same number field with much smaller coefficient, hopefully. So this is an example. We have this polynomial with moderately large coefficient, and if you do a Paul red best, you find this one. So you use LL reduction inside for the T2 norm in quadratic form. Okay, so this gives you the number fixed between this field and this field. So then, if you work with this model, with computation will be faster than with the larger model. Okay. So, okay. Okay, so now we can, we know to define polynomial for our field. We can define the fields themselves properly. So we need we have a function n infinite with this pre-computation. In particular, it computes the string of integers of the number field. Okay, so you do k equal n infinite of f, and so you get some structure. So you have k dot pol is the polynomial f, k dot sign is the signature. So here that means that there is two real embedding and one complex conjugate, two complex conjugate embedding. Okay, you have the discriminant of the number field, which is this. You have the integral basis, which is this. And so if you name W the second element of the basis, what does that say you? That the discriminant is this number, and that's the ring integer. It's this thing. You see. Okay, so sometimes we need to factor polynomial of a number field. So there's a technical point. you need to variable in PARI-GP have some priority, and if you want to factor a polynomial, you can only factor it with respect to the variable with the higher priority. So when you have number field, usually using x is not a good idea, because then there is no variable with higher priority than x. So here we will we will create a new variable with higher priority than x within var higher, we call it z. And so we will have polynomial in z, with coefficient will be element of k. Okay. And so what does that do this is that they evaluate k-pol in z. You replace the x in k-pol by z. Okay. And so you want to factor it, and you get this. So there is a 3 factor. So you can also have the roots of polynomial. So it's the same, but you use NF roots, so you can get the roots. And so in interpretation of this computation is that you see when you ask for the roots of a polynomial over itself, what you get is the Galois automorphism. And see x is will be so x is the identity, and this one will be alpha give 1 minus alpha. So the field is not Galois because the field is degree I don't know maybe, but 4, and there are only 2 automorphisms. Okay. Maybe I'm a bit fast. Okay. So now we can speak about elements of ideal. Okay, so there is 2 ways to represent element of number field. So either as we say using mod, or as element as a linear combination of the element of the integral basis. So usually, as is for small degree field, it's much better to use the integral basis because you get much smaller coefficient. Okay, so there is function in Al to basis and basis to Al to. Okay, so the only problem is that the integral basis is not canonical. I mean, the basis in some lattice and it's not canonical. And so, if you change of PARI-GP version, you might get a different basis. So all your computations are valid, of course, but the component of your vector will be slightly different because the basis is different. Okay. So, but on the other hand, if you use the mod representation, as long as your defining polynomial is the same, that the mod will be the same. I mean, it depends on nothing. So, okay. So this example was we asked what's the expression of the x squared on the integral basis, and we get that we get this 1 to 1. So if we remember that the integral basis one w alpha and w alpha, so we write down and we get this. Okay. And you have the converse operation, and F basis to Al to work backward. Okay. So we have a lot of functions in FL, mul, to deal with elements of number field. So NFL mul, NFL norm, trace. That will handle the problem of the integral. We allow element to be on the integral basis. So for example, this computes the product of this element writing the integral basis with this one written as a mod, and gives the result on the integral basis. Okay, and you can ask for the norm, the trace. So actually, if you had a mod, you could just do norm of mod of x minus 2 and the polynomial, and you get the norm one. But it would not work on the integral basis, and you would not know what the basis is. So you can also compute characteristic polynomial and a minimal polynomial. So here we have to convert it to the pole representation. And so as it says, the characteristic polynomial, the polynomial should be the same, except if your element lies in the proper subfield. When then the characteristic polynomial will be a power of the minimal polynomial. So here we find that this is the square of this one. So we can also compute the embedding, the real and complex embedding using NFL embed. So you get okay, you get this, and the order of the embedding is stored in K, so it doesn't depend. So every time you call the function, you get the same order for the embedding. You see. So this was for elements. So now we work with ideal. So first we have to create some ideal. So the simplest way is to factor prime number as product of prime ideals that give you some ideal. Okay. So there is function ideal prime dex that does that. So you give a k as the field and the prime number you want to split, and it gives you some vector. So each vector will one. The element will be the prime ideal. So there will be two. Here is two. So there will be two prime ideal. So you can do this. So that the first one is called PR1, second PR2. Okay. And you can ask for the f. The residual degree will be 1, and the ramification index here is 2. You can ask for a generator, PRgen, the generator. So that means it's generated by 5 on this element. Okay? And for PR, the second one, okay. So, okay. So if you want to have prime ideal, we might want to map to have the mapping to the residue field. Okay. So we have a function mod PR init to compute the mapping, and the function nf mod PR to apply the mapping. So the V is that you want the finite field generators to be V. Okay? So you do that, and then you do this, and so that gives you that the image of your element x1 plus x plus 1 in the field in the residue class in the class field. So, yeah. Which is, you see, P11F is 2. That's the field with 11 power 2 element. Okay. So you get this one, this element. And so this is a finite field element. So So when you reach it power 11, you get this one. And if you go it again, you take elements. And you can go the other direction using NF power PR lift that will find an element in the field that map to some element in the finite field. Okay. So this is for prime ideal. If you want more general ideal, we represent them by the Hermite normal form. So I did that. What's an ideal? It's a submodule of the ring of integer, and so it's in particular it's also a Z module of maximal rank. So it can be represented by a Z basis, and we can have the Z basis in Hermite normal form, and so that's why it does. That gives you the normal form of the Z basis. So this is understood over the integral basis, with respect to the integral basis. Okay? So that gives you 5. Okay, so now, for example, if you want to compute the HNF basis for a principal ideal, we just put the generator there. So it gives you the HNF basis of the ideal. And we can ask for the norm of the ideal. Get this. In this case, it will be the same as the norm of the element, as we have seen before, I think. Okay. So we have functions for operation of ideal. For example, multiplication or powering or addition. For example, if you want the cube of the ideal PR2, you can do this. This is the HNF basis. You can do addition of ideal. So here we get the norm is 1, so actually it's the principal ideal that we get. So the ideal are coprime. Okay, there is a fact that in a number field, ideal can always be represented by 2 generators, and there is a function ideal 2L that does that for you. So if you have an arbitrary ideal, it will find a representation with 2 generators. And so here, this is what it does, is that it additions the two principal ideal generated by each of the generators, and asks for the HNF basis, and we get the same basis for A. So we say that it's we have a correct representation for ideal. So we have some function ideal val to compute valuation with respect to a prime ideal. We have some function ideal is maximal to check whether an ideal is maximal. Okay. Yeah, and also the point also that you see prime ideal are represented different representations than general ideal. So if you have a maximal ideal, this allows you to recover, given by the HNF, I mean, this allows you to recover its representation as a prime ideal with the residual degree and the okay, so we also have factorization of ideal. So it's called a DDL factor. So they give you a matrix with two columns, which the first one is the ideal, second is the generators. And so in this case, we get that the ideal is divisible by 3 prime ideals. Okay. Also a point that you can also deal with fractional ideal. The only point that you will get a negative exponent when you factor them, of course. Okay, so when this command that tell you that the first generators, so it is above 2, it's residual degree 2, it's not ramified, and they appear with exponent 2. Okay, and the next one you see it's above 5, residual degree 1, it's ramification 2 and exponent 2. And you find the second one is clear 1 from the previous thing. Okay? Okay, so the third one is above 13. Okay, so we have the reverse operation, which is Chinese Allombert theorem. So you can do a Chinese Allombert theorem. So we have to do some factorization matrix and some element for each congruence class, and then you will find elements that satisfy the congruence. Okay, so here we will be equal 1 mod p1 square and minus 1 mod p2. So we get some element, you can check that the valuation is correct. So we have variant if you need sign. Sometimes we need a generator with prescribed sign. So you can compute the sign of the embedding of a number of algebraic number using NFL sign. And we can ask for a Chinese to give totally positive, for example, 1, 1. I mean, that means you want the sign to be fixed for all places. It's something important in, for example, in class field theory, often you have to specify which embedding you want to consider. So, if you don't want to, if you want to ignore some embedding, you put 0. Okay? So here we check the generator given is actually totally positive. While the previous one you found before was not, see -1. Okay. So the last part, class group on unit. So okay, so when you have a number field, there is notion of class group and unit group. And this is the computationally difficult part. Before, the only difficulty computationally part was you have to factor the polynomial discriminant. So sometimes it can be very slow and difficult to do this. But once it's done, normally everything is polynomial time, is nice. Okay. Here is different. So there is a function Beneffinite that does this computation. So you can give either an infinite or a polynomial. Okay. So here we give it the infinite we have, k. So k2, you check that. So we have nf component, which is the original number field. Okay. And no is the class number. So here is 1. So, and we have a regulator, k2.reg, which is this number. And the unit, so there are two kinds of units, the torsion unit and the fundamental unit. So k2.tu is for a torsion unit. So here we find there's only a -1 is only a torsion unit. And so we see that it's the same as asking the fruits of 1 of k, which makes sense. And the fundamental unit, so here there is two fundamental units. So they are more complex. So okay, this is a basis of the group of a group. So it's not totally canonical. I mean, it's a fundamental basis, but the units themselves are not canonical. We could could apply SL2 of Z and find a new basis for the same group. What's the method that generates the full group of units? So the class group. So okay, we try more interesting examples. We take this polynomial. Here we do L.seq, and we get 2, 2. So that means that the group is Z over 2Z times Z over 2Z. So this is the SNS, the Smith normal form of the group. Also, this PARI GP convention is to use dn divide dn-1 to divide d1. And so I think gap, for example, for Z over CZ, gap you often give 2,3. For the abelian group Z over CZ, usually gap will give you 2,3, while PARI GP will give you just 6. Okay. So you can have the generators, you get these two. This is actually HNF of ideal because it's the group is generated by the class of these two ideal. So we can test whether an ideal is principal using BNF is principal. Okay, so there is two components. DL is a discrete logarithm. So that tells you that the ideal is not principal, actually, but its class in the group is 1, 0. So remember, the class group was this Z over 2Z times Z over 2Z, two generator. So that gives you the component in this is 1 and 0. So if it was principal, it should have been 0, 0. The trivial element in the group. Okay? Well, it's for Borman, because it uses Borman algorithm. Okay, it's to say that we want to compute the class group and the regulator, and not just the integral basis. Okay. Okay. So what is J? J is it's a Wemmening generator. That is, if you have this, So if you take the generators of the group given by k.gen, so it's equal to the first element power 1 and second power 0, okay? But it's not will not be equal to pair. You will still have to multiply by j, because it's up to principal ideal. So this is generator of the principal ideal you need to add to get exactly what you gave in input. Okay. So this is the meaning of this slide. So you can check with this is computation. Well, okay. Also, the function ideal factor back. Well, it's a bit a strange name, but the idea is that the opposite of factors. I take a factorization matrix and do the product with the exponent to get the original result. So it's very useful because sometimes you have factorization, you want to change the exponent and refine the result. So you just need to change the exponent and call a factor back to get back. So here, that's the point. Okay. So we do. So okay. So we know that the class the class of an element is 1, 0. So we square it, we get 2, 0. But since it's mod 2 2s, it gets 0, 0. So the square should be principal. Okay. So we take the square of the ideal, and this time we get 0, 0. So it's principal. And G2 should be a generator. And we check that actually the HNF of the principal ideal generated by G2 is equal to the square of our ideal. So we are found the generator for ideal. So for the unit, it's the same. For here, we take this element, we can NF norm we find 1, so U is a unit. Okay. So you have function BNF is unit that tell you if something is a unit, and that expresses you the unit in terms of the fundamental unit. So here we get 1 to 1. Okay. So there's 3 components because the last one is for the torsion unit. Okay. And this means that we have expressed your unit U as this product. So the first fundamental unit times the square of the second one and times -1 power 1. Okay. So the only problem is that the fundamental unit can be very, very large very, very quickly. So you only compute them, benefit only compute them if they are small. So here you want to say it's too large, I don't. So it gives you 0 and not computed. Okay. So you can force it using benefit comma 1, which use the compact representation. So here we'll be able to do it. So for computation involving BNF is principal, it's usually a good idea to use this flag. And but most of the time you don't need to write down mf.fu. I mean, you don't need to know what are fundamental units, because usually they will fill hundreds of screens and meaningless. But they are stored in compact form as a product of S unit. And so you can still work with them without never having to actually compute the algebraic representation. Okay. So this is another example when it would work. You will still be able to print the fundamental unit, but we take hundreds of screens. Yeah. So it uses a Chinese number theorem to build the result. Okay. But there's a function BNF unit that will give you the fundamental unit written in terms of small element. So if you do that, you see that, but with large exponent. So that gives you that the frontal unit is equal to the some 37 elements of some set, but with exponent this. And this one with exponent this. So you see that it's compact, but because the exponent, adding one digit to the exponent doesn't increase the space on the screen a lot, but increase the number enormously. You can also have, unfortunately, very large ideal generators. So there is a flag, comma 4, which avoid writing down the generator explicitly only as a product of elements with exponent. Because otherwise you could get very, very large generators for the same reason. You can also compute S unit. The function BNF units when you can specify a second parameter, which is the set of place for your S unit. So S should be a set of ideal. Okay. So here, for example, you see you have the rank of the S unit group is 4. And then you can use benefit unit using by adding U as a third parameter to do the same as for benefit unit, but for the S unit. So to write some S unit as a product of the fundamental S unit. Okay. Maybe I was a bit too fast, but it was difficult. Yeah. So regulator is this one. This cat.reg gives you the regulator, and so it will be computed even if it does not compute the fundamental unit. It will still compute the regulator, because to compute the regulator, you don't need to have the algebraic expressions of fundamental unit. Only the numeric, the embedding. So what it does, if you use the comma 1, so we'll write your fundamental unit as product of number with large exponent, but it only needs the logarithm, and so it will need the embedding of each element, and then it takes the logarithm and multiply by the exponent and do the sum. So it can do this even if the exponents are large, since they only appear in the logarithm. No, I don't think the periodic regulator is implemented directly. You could be using the fundamental unit, but we did not implement it without computing the fundamental unit.
And higher regulators?
No, but okay, but you know about Karim program for K2, but the whole story. No. So
Further questions?
Just maybe in this PARI manage memory with respect to the question of Bettina earlier.
yeah.
About the fact that in fact in the history you only kept the commands and not the data related to the commands.
No, we kept the result. No, but the thing, in GAP, when you create an object, a group, if you do an operation on the group will grow. And so if you keep the group history, even if you don't need anything. In PARI-GP, you don't have the problem object doesn't. So you can keep them because I mean if you even if you enter one command every minute, 1 hour you only have 60 results, so it's not large.
Yeah, yes, but if you are space I described Renault yesterday, if you compute that, it will require maybe a lot of memory, and so if you keep it in the memory, it will. I mean, this is something which will blow a little bit.
Yeah.
Can you compute paranoid domains?
No.
Yes.
Yes.
Yes. Yeah.
But not with PARI-GP.
PARI-GP.
Yes.
Ah, okay,
You
okay.
don't believe.
Okay, okay.
Me, because I did it.
No, you did with GP, but not with the.
We did it for GL5 at the beginning. We did it with GL5 for GL5 in GP, not in.
Okay, okay.
So it is doable.
It is doable, yeah, okay. There is no function in GP for that.
As with GP, it doesn't.
Okay, so just to finish, I show you a bit more of the PARI-GP website. Okay, so there is a download package, everything, GP is your browser, but the only interesting is tutorial, because it's a list of tutorial for some topic in PARI-GP. So mostly we did algebraic number theory, this one. But there is another one which is advanced number theory. And some are video, and often thanks to Fanny. And yes, there is the deducting zeta function. Oh, you want that? Yeah, okay, I can do that. Yeah, I don't know where is the deducting zeta function. I think it should be in the L function, and it should be this one. Yes. Yeah. So I can give you an example there as you want. So, okay, so GP in your browser, up. So you take a number field. So I don't know what you want. It's cube minus 2. Okay, not very ambitious, sorry. So, and you can do often create of K. Okay, and so I should do that. Ah, il y a une faute de frappe. Okay. C'est bien la carré, non? Oh yes, I know. Je sais ça. Ah, il n'y a pas un exemple là. Ah bah non, the example is there, I think. Okay. So K infinite of this cube minus 2. Okay. So adding an create. Okay. So this is defines the deducting L function associate, and L fun params the. Okay, so we say that this is the L function of conductor 108, and with a gamma factor, so it's a gamma R squared times gamma R plus 1, that is gamma R times gamma C. Okay? So we can add the value at 2 maybe. -2, and if you want, -2. 0. -3, okay? And you can also divide it by the zeta function. So we do the dozen one with Elfen-div of L and 1. 1 is the code for the zeta function. There are a lot of code for the zeta function. And okay. So now we have the params. Okay, so now we have this the conductor is the same as u times. There is only gamma c and not gamma r, since we divided by zeta, so we move a gamma factor. Okay. And so now you can have the value at 1. If you have the value at 1 for L, then you get this. It returns the polar part. It's more a computational artifact than anything. It should resonate. Normally, it should say division by 0, but practical purpose, it's more usable if it gives you the polar part.